Okay. So now, in this the second part of the video, we're going to look at the design of steel columns and beams. Um, I'll hide the moments, and then in the in here in the design menu, go to steel members design options and code parameters. So this in this way, we need to now create the add the parameters to our beams, various design related parameters, and these are applying to all the beams. So we can click on the new and member type, maybe call it beam 1. So now in this um, in this dialog box, in this tool box, you can see various coefficients that you can specify, and at the moment the buckling coefficients in both directions are 1, and uh, that is what we can leave. This depends on the type of connection at each end. When the connection is pinned, the coefficient is 1. If it's fixed and pinned on another side, is 0.7. And if both ends are fixed, is 0.5. But here we are leaving it 1, which is going to be on the safe side. Now let's look at the flexural torsional buckling. If we tick that, the beams will be checked for flexural torsional buckling. In other words, if they will be failing in that mode. You may have not studied this yet, so just kind of we will just apply generally the parameters. The next one that we need to look at, the lateral buckling. So lateral buckling is depending on where the load level is. So we need to choose the third option here. We can choose the third option, which is the load at the sort of middle of the section. So this being the unstable and this the most stable location, we're choosing the middle one. Next, we need to click on the upper flange box, upper flange, and change it to the second option, L critical equal, third option, which is L critical equal to LO. Yes, there is 1, 2, 3, 4, 5. So, okay. L critical equal to 2LO, L critical equal to LO, which is the third option, as I can see here. And click OK, and then the same for the second option. Yes, sorry. And then the same for the lower flange. It's actually already selected, so I didn't have to do this. And then I repeat for the lower flange. So this is the lateral buckling length coefficient, depending again on the support at each end. So once you learn this in design, you will be able to choose the appropriate parameters. At the moment, we are choosing just general ones. Now we can click on the More button and look at the load type, and the load is in the Z direction. And we are choosing the second option, uniform loads simply supported beam. Uniform load, simply supported beam, and click OK. Next is to select the general method. So in the case, yes, so this is the lateral buckling calculation method, and it depends on whether the beam is restrained laterally. If it's not, probably the detailed method would be necessary. Next, we need to, because the beam, if it carries the rigid floor, such as a concrete floor, then it's not able to move laterally. Next one is to look at the service option. And here we can limit the beam deflection, and we will choose Z equals 200, which is already ticked, so we don't need to choose the lateral one in the Y direction, but this one we are choosing Z L over 200 from live load. So not the final one, but from live load. And click OK. So the deflection is limited, and then click on Save and Close. So this will save all these parameters for beam number 1, and then we can apply, save and close beam number 1, and then we need to apply this, just assign, apply to this part. And next, now we need to do similar thing with the column. Clicking on column and selecting new, we need to select now the various parameters that are relevant for the steel design of columns. And again, we click on new. We can call it column 1, this specific column with all the parameters that we're going to set. In the buckling coefficient in Y direction, click on the box and choose this one and click OK. So this means that the buckling coefficient will be calculated. By robot. The other ones we are leaving. The other one we are leaving as 1. Now for the serviceability, we can specify the limit on the sway in the Y direction, L over 150 nodal displacement. This is the sway of the frame in the direction perpendicular to us. and then we can click OK and save and close. So we can specify other limits if we wanted to, such as displacement in the Z direction. And now that we specified this column 1, we need to apply it to all the columns. So 1, 2, 12. Apply. Now that the member parameters have been specified, we can again calculate the structure. So using the calculator, and then we can open the steel design in the layout menu, steel design, steel aluminum design. And now we are going to click on the configuration, then change the number of points to 11. So this will be just making the calculation a bit more detailed. And the rest can stay as it is. So we have here member verification. For members 13 to 20, we can change it to 1 to 20. So all the members will be checked. 12 columns and 8 beams. And we're checking them for the ultimate limit states and serviceability limit states. And now we can click on the calculations, and this will show us our results, our detailed results for this frame. And we can see that some of the members have red X next to them, and these members, if you look at the ratio, they appear very high. Column 6, where's column 5 showing so high? That's very weird. The other seem fine. 580. So let's check column 1. Column 1 is failing. So what can we see for column 1? We can see that it has the axial force of 939 kilonewtons. Applied axial force. This is the design value, design axial force that the column can carry. And this bottom one is the design axial force reduced by buckling. So buckling axial force maximum for this column. And since this buckling resistance, design resistance, is lower than the applied design load, the column basically fails in buckling. Here we can also see that and we are checking this and this is for the most critical load case, which is combination 1. So for this case, we have a moment in this column relatively small, 4.6, and the maximum of minus 46, and this is the moment resistance of this column, 136, and then again I'm not sure what it is, and then the shear, applied shear force 15, and shear resistance of the column. We can see also class of the section is 1, so this is a plastic section. Lateral buckling was not checked, and then for the buckling in Y direction, the coefficient is calculated and the section is checked. So it is satisfactory in axial sense and shear, but in stability for buckling, using the formula for buckling calculation, the factor for buckling is 141, which is greater than 1, and that means that the section failed its incorrect section. So this section will have to be changed. Forces, we can see the summary of the forces at the column. Detailed, we can see the column description, and we can check various other stability parameters, such as web stability and so on. We can see the calculation note, which is sort of our design report. And yeah, so this is saying incorrect section. And parameters, that's what we have already done. So now let's look at the typical beam 13, which fails. Column 1, maybe I need to close this first. Not. View. There it is. Okay, so these were the results. And where are my results hiding? Do the calculations again, and looking at the beam 13. So now for the beam, it says incorrect section. Let's see what happened here. The applied axial force in the beam is quite small, obviously, and it can carry much larger force. The applied moment is 235, and the resistance of the section is 231, and buckling resistance, taking into account lateral buckling, is 151, and combination of moment and shear resistance is 227. So wherever you have a resistance RD lower than ED, that is a sign that the section has failed. And here, in terms of shear, the section is fine. Here is the check on lateral buckling, and it is basically slightly failing um, for moment and shear force combination. And but failing significantly in the buckling. So for the steel analysis, section has to pass with buckling as well. And if you look at the calculation note, it shows us all the various parameters, including the area, second momental area of the section, plastic and plastic modulus in both directions, various dimensions of the beam, and then the forces and capacities are summarized, and lateral buckling parameters. So now what we could do is just basically change the sections, increase the sections for a number of beams, because all our beams are failing and most of the sections are failing, and we also need to investigate. Okay, now it seems okay. The ratio, no, it still doesn't. So what happened to column 5? Column 5. No. Oh. Yeah, something is wrong for this particular column, so we may need to check it. Okay, so I'm not saving this. So what we can do now is go to our structure model, sections, materials, and choose a bigger section. So maybe for the column, I'll choose 305, 305, 198. And for the beam, I can choose 457, 152, 67, for example. Add and close. And I can apply the new section to bars 13 to 20. Yes. And new UKC section to bars 1 to 12, which are basically all the columns. And now I can recalculate, do the steel aluminum design calculations, and now if we expand this, we can see that the beams are still failing, but the columns are now fine. So we need to increase the beams even more. They're failing slightly, so the factors are quite close to 1. However, some of our columns are really not utilized now. So, but perhaps we could reduce the columns a little bit because the ratios should be really close to 1. Have I included all the? Yes, all the combinations were included. Okay, so this is the second video, design of a steel frame, and there will be a third one about steel connection coming up.